This curve has a minimum point when x is minus 2. So we're going to work it out in terms of k. dy by dx will equal 2x plus k, and then it's going to be plus 4 to the x to the minus 2. And this equals 0 when x equals minus 2. So that implies that minus 4 plus k plus 4 over minus 2 squared, because that's what x to the minus 2 is equal to 0. That's going to be minus 4 plus k plus 1, because when we square minus 2, we just get 4 is equal to 0. And therefore, that's going to be minus 3, so k is going to equal 3. So that means dy by dx is equal to 2x plus 3 plus 4x to the minus 2. We're now asked to show that the curve has a point of inflection which is not a stationary point. So for this we need to look at the second derivative, that is the gradient of the gradient. A point of inflection is when the curve goes from concave to convex or vice versa. So it's when the second derivative changes sign. And here it's going to be 2 minus 8x to the minus 3. Now my normal stance on this is to actually find out where the curve is concave and where it's convex, and then we can see the change in sign, because there are some issues when just setting it equal to 0. You can ignore some solutions because you can get a change of sign without it equaling 0 if there's a discontinuity. And if you do set it equal to 0, you have to check there is a change in sign. Now, if you try and turn this into an inequality, it's quite awkward because of x. I will show at the end how to do that. But here I'm going to set it equal to 0. It goes against what I normally do. So 2 minus 8 over x cubed is then 0. 2 equals 8 over x cubed. X cubed equals 4. So x equals the cube root of 4. Now we need to look either side. When x equals the cube root of 4 minus, say, 0.1, then the second derivative, I'm going to put it in. You could perhaps argue that it's necessarily going to be negative, but I don't think we need to be convincing here. So cube root of 4 minus 0.1. But that's my value of x, remember, so it's going to be 2 minus 8 over that, which is now my answer cubed. And we get a negative, minus 0.431. And we should just say that that means it's concave. Okay, what about when it's the cube root of 4 plus a little bit? Then it's going to be 2 minus we get 0.3349. So this is okay, as long as you show that there's definitely a change in sign, then we can use this method. Now, sorry, for that, I think I made a bit of a mess of that spelling. We were also asked to show that it's not a stationary point. So for that, we need to put it back into dy by dx. 2x plus 3 plus 4x to the minus 2. So we've got, cube root of 4. And then it's going to be 2 times that plus 3 plus 4 over the cube root of 4 squared. And we get 7.76. That is, that's important. That we're asked in the question, show it has a point of inflection, which is not a stationary point. So we've done the first bit, but we have to do this. Finally, I just want to show you what happens if you treat it as like finding where the curve is concave and convex, i.e. using inequalities. I kind of prefer this method, but it just is a bit too technical here to be to be useful. And I'm going to show you why. So we've got the second derivative is this, and it's going to be greater than 0 for convex. The problem is with this inequality, we can write it or we can divide through by 2, so it's 1 minus 4 over x cubed is greater than 0, and therefore 4 over x cubed is less than 1. But you can't just times through by x cubed actually, because it all depends on whether x is positive or negative. So let's say that x is greater than 0. So we have to split into these extra cases. We're already looking at this case when the second derivative is greater than 0. But in that case, we would get 4 is less than x cubed. And then x would be greater than the cube root of 4. So it's going to be convex here. Let's take a look at x is less than 0. Then when you times through by x cubed, you actually swap the sign around. So it's going to be 4 is greater than x cubed. And x is less than the cube root of 4. So overall, this means that if x is less than the cube root of 4 and less than 0, it has to be less than 0. So it will be convex for values greater than the cube root of 4 or less than 0. Let's take a look at convex. So then we get 2 minus 8 over x cubed is less than 0. Sorry, concave. Then we're going to follow through in the same sort of way, but we're going to get 4 over x cubed is greater than 1. It's going to work out in the same sort of way. So x greater than 0 is going to mean that 4 is greater than x cubed, and x is going to be less than the cube root of 4, or x less than 0 is going to mean that 4 is, you can just see how awkward this is, and x is greater than the cube root of 4. So I find that it's concave between 0 and concave 0 less than x less than the cube root of 4. There are no valid solutions here, see, because if x is less than 0 and greater than the cube root of 4, we just reject this, basically. Now, okay, that's taken a bit of time, admittedly, and that's why I didn't put it in my main solution. I just set it equal to 0, but it does reveal something. It first of all reveals straight away that there's a point of inflection at x equals cube root of 4 because it changes from concave to convex. Now, it also shows something going on at 0 though, because it also changes from concave to convex, depending which way you're going, at 0. So here, interestingly enough, the gradient does not equal 0, but it's actually not defined. And it is possible to get a point of inflection where the gradient is not defined. For example, the cube root function looks like this, and you get a point of inflection at x equals 0. However, in this case, the function itself is not defined at x equals 0, so there is no extra point of inflection. But I just, you don't want to rule it out. Might be a different sort of function that would have had a second point of inflection. So, look, I'm glad I went through this at the end, an alternative way of doing it. I do understand why this is not really covered in detail on the specification, like trying to just look for the change in sign, because ultimately, if you can set it equal to 0, and sure there's a change in sign, then it will be a point of inflection. And I think the syllabus just goes into that level of difficulty. But beyond that, I'm just trying to say that you can get points of inflection outside of that region, and that's why that's where the second method comes into its own, even if it is a little bit trickier to get your head around and implement. All right, well, yeah, I maybe overcomplicated that at the end, but ultimately we found the value of k, and we have shown there's a point of inflection that's not a stationary point. So I'm happy with that.